Okay, so hi everyone, this is the tutorial week 12 for the course thermal physics, and so this is the last tutorial. So this is mostly based on thermal radiation. So we'll solve problems which are practice problems again, and based on which you can get an idea to solve the current week's assignment. And after I finish these 10 problems of practice assignment, I will also discuss that how much time, according to how much time we have still left. I will also discuss some extra problems which will be useful for you to get the idea or concept of problem solving on this aspect. So let us start. So the first question is, wire of length 1 meter and radius 1 millimeter is heated via an electric current to provide 1 kilowatt of radiant power. Treating the wire as a perfect black body and ignoring any side effects. Okay, calculate the temperature of the wire given the Stephen's constant sigma value is given. So in the question it is said that there is a wire that you have to treat like a black body, perfect black body, and that wire's length and radius is given to you, and the radiant power it produces, that means how much energy per unit time it is producing when it is heated up by the electric current. That energy of the radiation per time is the radiant power, and which is 1 kilowatt as per the question. And the Stefan's Boltzmann constant, which is sigma, is given to you, so you have to calculate how much is the temperature of the wire. Okay, so as you can see from the question that there are very few standard type of choices that you have to make to solve this kind of problems, and you have to know some particular specific laws and formula, and out of them the most significant will be the Stefan Boltzmann's law of radiation. Okay, that gives you an idea of how much energy is radiated from a body, or maybe a black body, which has a connection to its temperature and the Stefan's constant sigma that is given to you. Okay, so I'll write that down and show you how that this thing is going to be solved. Okay, so one second. Okay, so question number where is that you have a one is that you have a where which is we have to treat it like a perfect black body. We can so as per the question. And the length of the wire is, let's say, capital L, which is it is given as 1 meter, and the radius of the wire is 1 millimeter, which if you convert into SI, so it will be like 0.10 to the power minus 3 meter, right? So now let's say this is your wire, so you can think of the wire like a cylindrical object, right? Because if you zoom in, so naturally you will have a shape of a cylinder. So this is, let's say, the wire, and this radius is R is equal to 1 millimeter of the wire, and the length, total length of the wire is 1 meter. Okay, so this is your wire in the shape of a cylinder. Okay, so now you have to hear, so sigma is given to you in the question. Okay, so that value is standard, so you can either, some questions they do not mention the value of sigma explicitly, so you have to remember the standard constant value, which is Stephen Boltzmann constant value is 5.67 into 10 to the power of minus 8, which is an SI unit. This is watt per meter square Kelvin to the power of 4. This is under the this division. Okay, so sigma value is given. So as per the formula of Stephen's Boltzmann law, there is an energy radiation formula, so that you have to use. So Stephen Boltzmann's law of radiation, it tells you that E is equal to epsilon A sigma T to the power of 4, right? Yeah. So epsilon A sigma T to the power of 4. So now you have to know that what are the different factors here that I have mentioned in the formula. So first of all, this is the value, left hand side E is the energy radiated per unit time. So basically this is the power of, this is the radiated power. So this is the energy radiated from the body per time, or this is equal to the power radiated, because energy per time is the power, you know that. And this A is the cross sectional surface area of that body on from which it is the energy is radiated, surface area of the body that is radiating the power. Okay, sigma is a reference constant which is a universal constant. Epsilon is the emissivity. Okay, emissivity is nothing but the ratio of how much the body is, has the capacity to emit energy in comparison to a perfect black body. Okay, so this is the ratio of radiated energy of a general body and to the maximum radiated energy from a black body. So if you take the ratio of that, that gives you the emissivity, or this italics or epsilon sign. So if the body is itself a perfect black body, so the ratio will be just 1, because if you compare a black body's emissivity or emission power with respect to a black body as standard, then the ratio will be 1, obviously, right? So for a perfect body of the object that you are getting, if it is taken to be a perfect black body, then obviously this emissivity epsilon will be 1. So epsilon equal to 1 for perfect black body. But if it is not a perfect black body, then it is not equal to 1, but it is less than 1. It is less than 1 for a normal body that is emitting power or emitting energy, because normal body does not have the maximum emissivity, because it will always emit some parts of the power, like the power absorbed by it or something that is incident on it. But for a perfect black body, it will emit the total energy that is present within. So that is why, or not total, but I'd say that is the maximum emissivity is from the for the perfect black body, and that is why epsilon equal to 1 here there. But for our case, because the wire is considered to be a perfect black body, so epsilon will be 1. And T is the absolute temperature, which is the temperature of the body that is emitting or radiating the power, right? So here, if this is the case, then you can see that you have to know the area, surface area for the wire, because this is the body that is radiating for our problem number 1. So for a cylindrical wire like this, you know that the area of a cylinder, cross-sectional body area of a cylinder is just 2 pi r times L. So this is the 2 pi r is from the radial part and L is from the length part. So surface area from this part of the wire, this is the area you have to take, because that area will radiate the energy, right? So this is the area, which is the formula is 2 pi r times L. Okay, where r value is given in the question and L value is also given in the question. So this is the area of the wire, 2 pi r L. So your energy emitted per time, or the power emitted, is in watt or joule per second. So an epsilon equal to 1. So here E is equal to 1 times 2 pi r L sigma t to the power of 4. So from here, if you have to take out what is T, then T is equal to just E by 2 pi r L sigma to the power of 1 by 4. This is the whole formula. And so in the question, you have to carefully now put all the known parameters that is given to you in the question. So in the question, E is given as 1 kilowatt. So E is the power that is radiated, which is like 1 kilowatt, which is like 10 to the power 3 watt, right? So you have to put that here. So this is 10,000 or 10 to the power 3 divided by 2 pi r is 1 millimeter. So this is 10 to the power of minus 3 meter. Into L is 1 meter, into sigma is also in SI, so 5.67 into 10 to the power minus 8 of the SI unit to the power of 1 by 4. Now if you very carefully do the calculation using your calculator, you will get an answer of T is equal to 1293.5, or almost you can say 1294 Kelvin. This is the temperature on the surface of the wire, which is the body that is emitting radiation in this question number 1. So the temperature of the wire or the black body in this case is 1294 Kelvin, which is option number B. I have already marked it. You can check that from the answer here that we are getting option number B, and that is the correct answer. So this is how the general problem number 1 can be solved. Now question number 2, let us move on to. So it is saying that a cavity radiator has its maximum spectral radiance at a wavelength of 1 micron. 1 micrometer in the infrared region of the spectrum. The temperature of the body is now increased so that the radiant intensity of the body is doubled. Now the power temperature would be how much? So in this case you see there is a cavity radiator, so there is a black body radiation sort of a thing going on, and this word, that maximum spectral radiance, this itself tells you that you have to take the how do you take the maximum radial spectral radiance. So there is a, for black body there is a spectral radiance versus temperature plot that is known to us. So how with the temperature increase the spectral radiance will decrease. There is a particular pattern sort of for that, but for different temperature that nature shifts very slightly from each other. So basically still if that is the case, then you have to take out what is the temperature of the body when the radiant intensity of the body is doubled. Okay, so earlier the intensity was something and now the radiant intensity of the body has doubled, so you have to take out how much the temperature of the body has changed, or in this case will be increased, because only if the temperature is increasing then only the radiant intensity of the body will be increasing or doubling. So now the temperature would be what? So this is the question given to you, and we learn how to solve this kind of a problem. Okay, so we are at the second question. Now here we consider that the cavity radiator, that is the object that is emitting the radiation in this case, and there is a mention about the maximum spectral radiance with some wavelength, right? So this immediately tells you, whenever you see that maximum spectral radiance, this terminology is used, you have to understand that it is most likely will be solvable by using the Wien's displacement law, because that involves a maximum of the wavelength where the spectral radiance is a maximum, and its relation with temperature. So we'll be seeing what is the formula of Wien's displacement and how we can utilize it to solve the problem number 2. So problem number 2 has this cavity radiator which is radiating energy or power or whatever radiation, emitting radiation, and maximum spectral radiance, maximum spectral radiance for that cavity radiator is at a wavelength lambda equal to lambda subscript m. So lambda m, this subscript mean m actually signifies that here the spectral radiance is maximum at this particular wavelength. Okay, and the temperature is equal to T Kelvin in this case, let's say. So then Wien's displacement law is there, which tells you that lambda m into T equal to constant. Okay, so as per Wien's displacement law, the formula, the rule is that lambda m into T is equal to constant equal to B. Let's say the constant value is B we have taken, and this B is basically a constant, standard constant, of which the value we know about. Okay, so B is equal to 2.897 into 10 to the power of minus 3 meter Kelvin. Let's say whether the question has the information. Yeah, they have mentioned the value of B in the question, but sometimes they do not mention it. So it is also necessary to, it is best that if we remember the standard constant values, like we have to remember the Stephen's constant, that is sigma. Similarly, we can remember what is the value of this Wien's displacement formula's constant, or Wien's constant B, which is this value, because sometimes the question does not mention it explicitly, but you have to remember it on your own. But mostly they mention it, but we'll prefer to remember this constant value. So this is this B value is given in the question, so we have taken that value from there. Okay, and it is said that the temperature when it is increased, so the radial intensity is doubled, and lambda m, where the radiance is maximum, spectral radiance is maximum, is equal to 1 micrometer. Okay, so this thing, this lambda m is equal to 1 micrometer is mentioned, which is like 10 to the power minus 6 meter. Okay, so now I can quickly draw what is the basic structure from where we are taking out this Wien's displacement law formula. So if this is the y versus x axis, let's say on the y axis there is this spectral radiance, and along the x axis there is this wavelength lambda. Okay, so if that is the case, then how will be the graph, how will the graph look like? So initially this will be something how the spectral radiance versus wavelength graph will look like. Okay, so this is at, let's say, lambda m1, and this is at temperature T1. So you can see that this is the maximum of the spectral radiance, that is the peak of this curve, and this maximum occurs at a wavelength value of lambda m1 in this case. So this is the wavelength that which spectral radiance is maximum, or that is why we identify it at lambda m1. But this is for the temperature of T1. Now if you change the temperature, then the curve will not remain the same. The curve will also shift. Okay, and how much it will shift? So basically how it will shift, the trend is that as you increase your temperature, your as you increase your temperature, your lambda m value decreases. So that is why if T1 is, let's say, a higher temperature where the lambda m is equal to lambda m1, then for lowering the temperature, that means when you lower the temperature value less than T1, so necessarily the maximum at which the peak occurs will get shifted to the higher wavelength value. So how will that happen? So we can draw another curve where I am using this blue to draw this. Sorry. If we draw another peak from this position, line from the peak position, so it cuts at the wavelength of lambda m2, let's say, and this is for temperature of T2. Okay. Similarly, if you have another one, so if you have another one, then it will also follow the same thing. 1 second. Space note. Just 1 second. Yes. So, and the third one will be like, let's say I'm drawing now with red. This is just different colors to identify the temperatures differently. And here also through the peak, we draw a line which will be at lambda in 3 and the temperature is T3. So what is the relation in this case is that your T1 is greater than T2, which is greater than T3. So T1 is the highest most temperature in this case. So as a result, lambda m will have an inverse proportionality relation to T. So basically for T1, lambda m1 will be the minimum. So lambda m1 where the peak value occurs is the lowest one, and then lambda m2, and then the highest one is lambda m3 because there the temperature is the minimum. So you see that as per Wien's displacement law, as temperature decreases, the wavelength at which spectral radiance is maximum shows a peak that is at lambda equal to lambda m. As temperature decreases, lambda m shifts to higher value. Okay, that means if T increases, lambda m decreases, and if T decreases, then lambda m increases. Okay, so this is the idea. And in this, throughout this process, so this lambda m is basically inversely proportional to T, or it is proportional to 1 by T. Okay, because if temperature decreases, it increases, so it has an inverse proportionality relation, and from there we get the Wien's displacement law, that is lambda m into T is equal to constant is equal to B, which is Wien's constant. So this is the Wien's displacement law. Okay, now from here, because we have the information about lambda m and we have the constant value B known, so we can calculate or take out the T value of the body, the temperature of the cavity radiator we can take out by using this Wien displacement law. So T is equal to just B by lambda m. B value we can know from the question, so it is 2.897 into 10 to the power of minus 3 divided by lambda m is also given in the question as 10 to the power of minus 6. So you can use your calculator and you will get this is 2 point, or this may not need calculator only. So this is 10 to the power of 3 Kelvin as your T. So this is, let's say, this is the temperature uh, of the cavity radiator when lambda m value is given as 1 micrometer. So this is the initial temperature, let's say initial T1 when lambda m is equal to 1 micrometer. Okay, initial temperature. Now it is mentioned in the question that if you double the radial intensity energy, how much the temperature will change and what will be the latest temperature value. So let's say your temperature has now changed in a process. Temperature changes. So T1 it goes to T2. Okay. And T2 is greater than T1. But we do not exactly know what is T2, but we know that T has increased. So T2 is greater than T1 in the last or final, in the final value of temperature. And another connection is given there that your radial intensity also becomes double of the previous radial intensity by this temperature rise. So radial double. That means, so radial energy intensity basically means that the energy, how much energy is radiated per unit area, per unit time. So this you can know from Stephen Boltzmann's law, that how much per unit time. So that is radial intensity. Let's say we call it P. So P will be like sigma T to the power 4. Okay. Actually, it is P equal to epsilon sigma T to the power 4. But epsilon equal to 1 taken, assuming the cavity radiator to be a perfect black body. Okay. The cavity. However, if even if epsilon value is not 1, it is even if less than 1, then also we have no problem with that, because we just need the relation between the radial intensity at the temp and the temperature. Okay, we don't need the exact form over here for our requirement. So this is Stephen and Boltzmann's law, as per which you can see the relation between, so let me divide this. So the relation between the radial intensity and the temperature is like going like this, that P varies as T to the power of 4, or P is directly proportional to the fourth power of the temperature. So if that is the case, then let's say it is mentioned that the final radial intensity is double of the initial radial intensity. Okay, when T1 goes to T2, then P2 is equal to double of P1, or 2 times P1. Then how will that happen, or how will that change the temperature value exactly? So by this form, P2 by P1 is equal to T2 by T1 whole to the power of 4. So T2 by T1 will be like P2 by P1 to the power 1 by 4, or T2 equal to T1 times P2 by P1 to the power of 1 by 4. So T2 equal to simply T1 times P2 is equal to 2P1. So 2P1 by P1 to the power 1 by 4. So T2 equal to will be T1 into 2 to the power of 1 by 4. So we know the T1 value because it is we have calculated from using the Wien's displacement law. So this is 2.98897 into 10 cube Kelvin, which is like 2897 Kelvin. So we'll use that here, 2897 into 2 to the power of 1 4. This is your T2 value, which is like, you can use your calculator and get the value, that this is 3445.13 Kelvin. So this is the final temperature, option number D. So let's check. So we are getting 3445, which is close to option number D. So option number D is the correct answer as well. Okay, now question number 3 is about the pressure inside the sun is estimated to be of the order of 400 million atmosphere. Estimate the temperature corresponding to such pressure, assuming it to be resulted from radiation. Okay, so firstly, it is talking about the pressure inside the sun, and also mentioning explicitly that the pressure is resulting from the radiation. So it is not some other pressure, because then the definition will be different. But there is a particular kind of formula for radiation pressure, or pressure of radiation. So it is important to mention that here this pressure is coming from the thermal radiation inside sun. So we'll see what the formula is, and also the pressure value is given, and you have to calculate the temperature. So P equal to pressure, which is caused by radiation inside the sun. And this pressure value is also given as some 400 million atmosphere, right? So 400, this we have to take into SI unit. Atmosphere is not SI unit because otherwise the formula, mathematical formula will not be in the same unit. So that is why we convert into Newton per meter square, which is in SI units of pressure. But first of all, million, 1 million is 10 to the power 6. So 400 million is 400 into 10 to the power 6, which is like combining these two zero together with 10 to the power 6. So this is 4 into 10 to the power of 8 atmosphere, which is like 4 into 10 to the power of 8 into 1.013 10 to the power of 5 Newton per meter square. So this is the pressure value inside sun. You can see how enormous is the pressure is, because sun is compared to it is sun, that obviously the value will be quite huge. But rest of it, that we have to use the formula of pressure of radiation. So pressure of radiation of an object P is equal to small u by 3, equal to small u by 3, where P is the radiation pressure and U is the internal energy density of radiation, which is like capital U by capital V, where capital V is the volume of the object and capital U will be the internal energy okay. And this U has a formula that U equal to A T to the power 4, okay. How energy density is related to temperature, again T to the power 4, but A is here an integration constant which has a particular value as per the calculations already known to us. So we'll be directly using that A equal to 4 sigma by C, where sigma is a Stephen's constant. So from here we can see that U equal to 4 sigma T to the power 4 by C, okay. So then what is T from here? T is equal to, sorry, no, we have to go further, that P is equal to U by 3, right? So P equal to now 4 by 3 sigma T to the power 4 by C, okay. So then what is the T value? T value is simply 3 P C by 4 sigma to the power of 1 by 4. So this is the value of temperature T, and here now we have to substitute the known value so that we can get the value of temperature. Like P value, we just saw that this is 4 into 10 to the power 8 into SI unit conversion, so 1.013 into 10 to the power of 5. C is the speed of light in vacuum in SI unit, so it will be like 3 into 10 to the power of 8 meter per second. So this is divided by 4 into sigma. Again you have to use the value of the Stephen's constant. So here, like, the question does not mention the Stephen's constant by value, but you have to remember it, so you can use it here. 5.67 into 10 to the power of minus So this we can combine this together and get the calculation done, that T equal to 2 into 10 to the power of 7 Kelvin. You can see how huge is the temperature is, 10 to the power 7 order, but this is the so this is the temperature of the sun that you have to calculate from this question. So this is option number A, you can check. And sigma is a Stephen constant value. I can mention here that 5.67 into 10 to the power of minus 8. You can check what is the SI unit of sigma, but this is the SI unit value. So with this we also solve question number 3, and the correct answer we get is 2 into 10 to the power 7, which is also the accepted answer. Okay, so this is also covered. Then we'll see what is question number 4 asking us to do. That an iron ball is having a surface area of 100 centimeter square and a temperature of 527 degrees centigrade, and it is placed in an enclosure at 27 degrees centigrade. If the surface emissivity of iron beam is 0.3, at which rate is heat being lost by the radiation by the ball? So question number 4, and it is about iron ball surface area So this is, you can say, converting into meter, 10 to the power minus 2 meter is equal to 1 centimeter, but it is squared, so this is 10 to the power of minus 4 meter square. And the temperature of the iron ball T is equal to 527 degrees centigrade, which is like 527 plus 273. And the outer, or the box in which the ball is kept, I think that box was mentioned. So yeah, the enclosure in which the iron ball is placed is at a different temperature, 27 degrees centigrade. So let's say it is T naught. It's 27 degrees centigrade, which is converting into Kelvin is 300 Kelvin. So this is your box. At T temperature, and the enclosure in which it is put, and enclosure temperature is T naught. So T is not equal to T naught first of all. Now it is asking that how much will be the energy loss by radiation by that iron ball. Okay, so we can consider in the sake, for the sake of solving this question, that because there are two temperatures mentioned, so we have to consider that the iron ball, which is a black body assumed in this case, is in contact with, or is in the surrounding of this enclosure, which is at a different temperature, which you can also consider as a black body type. So basically one black body is in contact with another black body in correspondence with another black body at a different temperature, and if they are in contact with each other, then the energy loss, that is by radiation, will have both the temperature values present. So which are two black bodies, which are iron ball and enclosure, which are in thermal contact. So in such cases, if the temperatures are different, then the energy loss by radiation is taken as Q A is equal to A epsilon sigma T to the power 4 minus T naught to the power of 4, where A is the surface area of the iron ball and epsilon is the surface emissivity. So here you can now compile everything and get QA. So QA is equal to so the surface area was 100 into the power minus 4 meter square. So this is 100 into the power minus 4 meter square. Surface emissivity is given epsilon as 0.3. Sigma value you have to remember, this is 5.67 into 10 to the power of minus 8 into T and T naught values are given. So T is 800 Kelvin, which is 800 to the power of 4, and T naught is 300 Kelvin, which is 300 to the power of 4. So from here you get QA is equal to 68.2 joule per second, because it is always in per unit time units. So 68.2 joule per second means, if you now convert into calorie, as per the question the answers are given in calorie. So 68.2 divided by 4.2 calorie per second, because 1 calorie is equal to 4.2 joule. So 1 joule is equal to 1 by 4.2 calorie. So if this is the case, then by dividing it you get that this is 60 calorie per second is the heat energy, or that is radiated by it. So we mark this down, that this is, we have got 16, right? So 16 is close to this value, 16.2 calorie per second. So this is also the accepted answer. So with this, question number 4 is also done. Okay. Okay, so now we look at the question number 5, which is about a spherical black body with radius 12 centimeter. Okay, so a spherical black body with radius 12 centimeter radiates 450 watt power at 500 Kelvin. If the radius were halved and temperature doubled, then the power radiated in watt will be watt. Now, a spherical black body is given, so its size is given in terms of its radius r, and it is said that it radiates the power of 450 watt, that means joule per second. Power means energy per time is given, and the temperature is given as 500 Kelvin. If the radius were halved, if r is made r by 2 and the temperature is doubled as 2T, then what will be the power radiated in watt? Now here you can see that you have to use the Stefan-Boltzmann law for energy radiated or power radiated, and based on that you have to solve this problem. So let us now go and solve this. So question number 5, we have a spherical shaped black body, and it has a radius r of 12 centimeter, right? So r of 12 centimeter, and which is like 12 into 10 to the power of minus 2 meter. And the temperature of this body is right now 500 Kelvin, and the heat power it radiated, power radiated equal to, so we denote it by E equal to 450 watt. So as per Stephen Boltzmann's law, we know that E equal to epsilon A sigma T to the power 4. Now because it is said that it is a black body, so we will consider our epsilon to be 1. Okay, so then it is just A sigma T to the power 4. A is the surface cross sectional area and sigma T to the power 4 is the energy per area per time. So if that is the case, when you multiply that by area, so you are getting energy per time. Okay, so now you have that 450 watt or 450 joule per second is equal to, you have to know what is the area of a sphere. So area of a sphere is simply 4 pi r squared. So this is 4 pi 12 into 10 to the power minus 2 in meter radius r squared into sigma is 5.67 into 10 to the power of minus 8 into t to the power 4 is 500 to the power of 4. Okay, so here rather we would have to take out the value of sigma and then use it. So because sigma is not standardly given in the question. Okay, or the other method can be that it is, because it is like this the formula, so epsilon is proportional to A and epsilon is proportional to t to the power 4 as well. Otherwise this is 1 and this is constant, right? So nothing else matters. So epsilon is directly proportional to actually A to the power 4, and A, you know that area is proportional to r square for a sphere. R square is the radius r. Okay, so that is why E will be also proportional to r squared t to the power of 4 from this formula. So what we will have is that E2 by E1, take the ratio, is R2 by R1 whole squared into T2 by T1 to the power of 4. So radius is half, that means R2 is half R1, so this is like this. Okay, and temperature is, I think, doubled. So this is 2T1 by T1 to the power of 4. So what you get is that half squared into 2 to the power of 4. So this is 2 to the power 4 by 2 squared, which is like 2 squared equal to 4. That means your E2 is equal to 4 times E1, or if E1 is given as 450 watt, then it is simply will be 1800 watt, which will be your answer. Okay, so let us choose the answer. It will be option number what? So it is option number D, which is the correct answer we obtained. Now question number 6 is calculate the pressure exerted by sunlight on Earth's surface given that the solar constant or intensity of radiation is some 8 point something joule per centimeter square per minute. Okay, so energy, the radiated energy per area per time from the sun is given by this term called solar constant. So solar constant is also called as intensity of radiation. It is the energy per unit time per unit area that is coming from sun to reach the earth. Okay, so it is solar constant. So now from there you have to calculate how much, because of this radiation, how much pressure is the sunlight exerts on the earth's surface. Okay, so the trick for solving this is that question number 6, So there is a straight cut formula of pressure relating the intensity. Okay, so how do you do that? So you know that pressure P is equal to pressure of radiated energy on a surface. It has the same dimension as the energy density. It is the same as the energy density U, because energy density is what? Energy by volume. Okay, so energy is basically work done. So work done will be force into displacement, let's say F into L, and volume is L cube. Okay, so it is basically being F by L square, which is like force by area, F by A, which is as pressure. So that is why you see the dimension wise also pressure is equal to just the energy density, energy per unit volume. Now we have a direct relation of pressure to the intensity as well. First of all, how do you define intensity here? So intensity or the solar constant in this case has this unit of joule per centimeter square minute, I think. So it is basically energy by surface area into time is E by A into T, right? So to get your P from here, you see that in your P there is only energy density, right? You have to have, for P you had to, let's say intensity we define as I. Okay, I is not current, I is the intensity here, which is this. But to get pressure, radiation pressure, you know that the formula is energy density's dimension, which is like energy by volume. That means it should be E by A into length, so that it becomes E by V, volume. But here in the intensity you have E by A into T. So how to connect these two? So you can see that if you divide your I by C, which is the velocity, length per time, so then you have previously I equal to E by A into T, and C becomes 1 by C becomes 1 by L by T. Length by time is the velocity. So this time and this time cancelling out. So you are simply having E by A into L, which is area into length, is the volume. So there you have your pressure, which is the same dimension as intensity by speed or velocity. So in this case, because sunlight we are talking about, so C will be the velocity of light. Okay, sunlight in this case. So simple formula is P equal to I by C, where P is the radiation pressure, I is the intensity of radiation, and C is the velocity of light. So there you have that intensity is equal to, now it is given that of sunlight intensity radiation is 8.148 into 10 to the power 4. It was what? Joule per meter squared minute, right? But you have to have joule per second, so you have to convert that minute into second. So divided by minute means 1 minute equal to 60 second, right? So just this is 8.148 into 10 to the power 4 divided by 60 joule per meter square second. So this is your intensity. So intensity by speed of light you have to get. So 8.148 into 10 to the power of 4 divided by 60 into 3 into 10 to the power of 8. this is your value of pressure, and this is, if you calculate, this will be 4.52 into 10 to the power of minus 6 Newton per meter square. So this is the idea. So this is the pressure value. Now let us check whether it matches. So we are getting uh, 4.52 into 10 to the power of minus 6 Newton per meter square was the value you are getting. But if you have to convert it into Pascal, so then you have to 4.52 into 10 to the power of minus 6 divided by 1.013 into 10 to the power of 5. This is not the case. So, oh no, so basically Newton per meter square is same as Pascal, right? So 1 Pascal is equal to 1 Newton per meter square. So that is why you get the value, whatever value you got or we got is 4.52 to the power minus 6 Newton per meter square, or Pascal is the same answer. So C is the correct answer that we obtained. Now, question number 7 is the absorptive power of a black body at red and blue light are respectively given as A red equal to something and A blue equal to something, given in watt per meter squared. So, energy per time per area. Find the ratio of emissive power at red and blue light. Okay, so basically here you have to use the Kirchhoff's law for this emission case. So let us solve it here only. Kirchhoff's law tells you that if you take the ratio of emissive power, it will be the same as the ratio of absorption power, because emission is actually directly connected to absorption. If a body is a ideal emitter, then it will also be an ideal absorber. Okay, so that was the idea that was given by Kirchhoff's law. So if you have two lights, red and blue light, and if you know the ratio of their absorptive power, let's say A red by A blue, then it will be the same as the ratio of the emissive power, which is, let's say we call the emissive power given in terms of E. So E means the emissive power. It will be the same as E red by E blue, because this is directly proportional to absorptive power is directly proportional to emissive power. That is why A red by A blue is equal to E red by E blue. Okay, so this is equal to A red is 300 watt per meter square divided by A blue is 400 watt per meter square. So this is 3 by 4 simply. So E red by E blue equal to 3 by 4. So the ratio of absorptive power is the same as the ratio of emissive power, because they are directly proportional, and the ratio value is 3 by 4, which is the correct answer. Now this is a conceptual question in question number 8, that close to absolute zero temperature difference between the specific heat goes to what? So if the temperature is going to absolute zero, then what will be the difference of the specific heat value going to? So this value will be 0 first of all. How it is 0, that I am going to show you afterwards. So let us do a little derivation, that all this is coming as a consequence of the third law of thermodynamics, right? So it says that if your entropy difference you are talking about, so entropy difference is delta S, which is S of T2 minus S of T1. Temperature difference T2 and T1, and this is simply because specific heat, if you talk about specific heat, is simply T ds dt, right? So then from there delta S will be like 1 by T Ct dt, right? So from there you get that this is your Cx, let's say, dt by T from a temperature of T1 to a temperature of T2. So here X can be either volume or pressure. So then now if T1, let's say any of the temperature is going to zero limit, then the third law, if the third law to be valid, it demands that the integral needs to be finite and not diverging, right? So that requires both the specific heat Cx to be 0, tending to 0, as temperature tending to 0, because for delta S to be finite and not diverging or not anything, so for third law of thermodynamics to be valid, so if temperature both here is 0, let's say temperature is 0, then so that this whole thing does not become like diverging or undefined anyways, so that is why we also have to take this upper the numerator part, which is this Cx tending to 0. We need Cx tending to 0 as T tending to 0. This Cx can be either Cp or Cv tending to 0 as T tending to 0. Now we define another thing, which is this alpha. Alpha is the volume expansion coefficient, which is minus 1 by V del V del T, not minus, plus 1 by V del V del T at P constant. But from Maxwell's four laws, or Maxwell's laws of thermodynamics, so Maxwell's laws tells you in one of the conversion that del S del P at T constant is equal to minus del V del T at P constant. So substituting that, alpha is equal to minus 1 by V, then del S del P at T constant. So if delta S tends to 0 at T tends to 0, because third law of thermodynamics tells you that at absolute 0 temperature the entropy difference will also tend to 0. Okay, that means it should not be diverging, and for that we needed to have, as T tends to 0, C should also tend to 0. But now in case of alpha, you see that at T tends to 0, third law tells you that delta S should be going to 0 for all P values. So if that is the case, then alpha also tend to 0 as T tend to 0 for all pure state. Remember, all these conditions we are taking are all for assuming that it is in the pure state. Okay, now so we are getting the specific heat difference Cp minus Cv. Now this difference, there is a formula that we derive from the Maxwell's relation and FD connecting formula, that you can find out. If you do not remember, you can go back in maybe a few weeks lecture earlier and you can go back and check from there. We even solved a tutorial problem based on that what will be the value of Cp minus Cv. So I will be directly writing that value now. So Cp minus Cv has a expression that it is Tv into alpha del P del T at V constant. So this is proved from before, so I am not going to show the proof again here. So here alpha is the volume expansion coefficient and rest of the terms are as per the standard form. So now as temperature tends to 0, so we see that we have already seen that alpha will also tend to 0, right? Now volume, this is non-zero because it is a finite volume, and with temperature change there will be also pressure change, so this is also not diverging. So you are seeing that as temperature tends to 0 and alpha tends to 0 on right hand side, so that makes LHS the left hand side tends to 0, or Cp minus Cv, the difference in the specific heat is tending to 0 as temperature tends to 0. This is question option number C that we are getting. So we have obtained the correct answer. Now question number 9 is calculate the ratio of specific heat at constant volume and absolute entropy for a cavity maintained at 1000 Kelvin. Okay, so ratio of specific heat you have to calculate, and not specific heat but ratio of specific heat at constant volume of CV and the absolute entropy S. So CV by S you have to calculate for a cavity which has a temperature of 1000 Kelvin. Okay, so basically you have to use some expressions. For this you have to separately know what is the specific heat at constant volume and what is the entropy expression, and then take a ratio of both of them. So as per that, question number 9 is that you have CV by S equal to what? So first of all, for a cavity, assume it's a black body, right? So then if that is the case, then your U total energy is equal to energy density small u into volume, right? And you know that this small u has a expression u equal to a to the power 4. A is an integration constant. So then capital U will be AV t to the power of 4. Then specific heat C is del U del T at V constant, which is like AV 4 TQ. So then if this is C, so specific heat you have obtained. So this can be CV because this is exact expression of specific heat. But now if you derive further, so CV has expression like T del S del T at V constant, which is equal to what? 4AV TQ. So from there, del S del T at V constant is just 4AV T squared. Right? So here if you take ST will be like 4AV T cube by 3 by the integration. So we avoid the integration constant and anything. So directly by getting these and these expressions, underlying expressions, we take the ratio of CV by S, which is 4AV T cube divided by 4AV T cube by 3, which is equal to 3 is the ratio answer that we get. So this is option number. Let us choose the correct answer. So this is option number C, right? Correct answer is also C. Now this is also done. So last question is question number 10, that a cavity with volume of 5 liter is maintained at 4000 Kelvin. For the system, calculate enthalpy. Okay, so cavity with a volume of 5 liter is maintained at 4000 Kelvin. For the system, calculate enthalpy. Now enthalpy is H that you have to calculate. You have the information about the cavity volume V and the cavity temperature T. You have to know what is H. So let us solve this. So you have a cavity which is same as, you can consider that it is also a black body. Okay, so you know that you have to calculate the enthalpy. So enthalpy is H. H is a thermodynamic potential chapter you have obtained. You have learned about that. H is expressed as U plus VV, where U is the total internal energy, P and V are the pressure and volume. Okay, so this capital U will be also small u times capital V, energy density times volume. And P is the pressure due to radiation, so it is U by small u by 3, where U is the small u is the energy density, right? So A is equal to U times V plus U by 3 times V. So this is 4/3 U times V is your enthalpy H. So this is 4/3 enthalpy is A to the power 4 times V, right? Because you already know that your U is A to the power 4. You have to use this, and expression of P you have to use. Else you know everything. So this is, you have obtained directly that it is A to the power 4 times V. Now A value we have to put here because A is the integration constant, which is expressed as 4 sigma by C, where C is the velocity of light and sigma is the Stefan's constant. So this is just A, it is just 4 by 3 into 4 sigma by C to the power 4 into V. So this is just 16 sigma to the power 4 into V by 3C is equal to your H. Now you have the information about volume and everything. You put the directly the Stefan's constant value, which is like 5.67 in 10 to the power of minus 8 in SI unit, divided by 3 into T to the power 4 is basically temperature was given as 4000 Kelvin in the question, and the volume was given as 5 liter. So 5 liter can be in SI, it should be meter cube. So 1 meter is equal to 10 decimeter. So 1 and decimeter cube is liter. So you have to convert it like 10 to the power of minus 3 meter cube. So T to the power 4 is just 4000 to the power of 4 into V is 5 into 10 to the power minus 3 divided by 3 into 10 to the power of 8. So this is just 1.29 into 10 to the power of minus 3 joule is your answer that we will obtain from this calculation. So this is question option number C that we will obtain from here. Okay, so you are getting option number C, I said, because we are getting 1.29 10 to the power minus 3 joule. So this is basically 1.29 millijoule. So this is also the correct accepted answer. So with this we are finished with the practice assignment problems for this week. Okay, so since we are done with the practice assignment problems, as I said that I'd like to solve some extra problems which will be relevant for the similar kind of problems given in thermal radiation chapter. So let us take a look at that quickly. So just some highlights problems that I think will be relevant. So problem number 1 is, assume the earth is a spherical black body, which is because you know that earth is moving in a circular radius around the sun, right? So now consider earth to be like a spherical black body, and it has the radius in which the orbit in which it is revolving around the sun it has a particular radius which is known to us. Now find the equilibrium temperature if the sun is considered to be also a sphere of radius of some radius is given, and it is also radiating like a black body at some temperature given in the question. Now assume that the Earth's radius is very small compared to the radius of the orbital around the sun, and find the equilibrium temperature of the Earth in this case. So let me just write down the question in short so that you understand that we have sun, right? We have sun, and around that, if you just, so the orbital is not, so consider just that Earth is revolving in orbital around the sun. Earth. And consider both of them are like two black bodies. Consider both are two black bodies. Now there is a particular radius, because all of them are in spherical shape we have assumed. So the radius of sun is certain, and radius of earth is some other value. And similarly, the radius of the orbital around which the earth is moving around the sun, that is also considered as a circular orbital, and that radius is taken as capital R. And the radius of the sun is taken as rs, and the radius of the earth is taken as, let's say, re. Okay, and the temperature on the sun is given, which is temperature of the sun is given as Ts, which is given as 6 into 10 cube Kelvin, right? And the radius of the sun is given as 5 into 10 to the power of 5 kilometer. Radius of the orbital in which the earth is moving around the sun is capital R, is given as 1.5 into 10 to the power of 8 kilometer. These are the options no information given to you, and I also mentioned that the Earth's radius Re is much less than small compared to the radius of sun. This is the orbit's radius. Now based on this you have to find out the equilibrium temperature on Earth. So TE equal to what? Temperature on Earth. Now basically it is a black body problem, because we have assumed that both the Earth and the sun are the two different black bodies in this case, and the black body that is emitting the radiation here is the sun, and Earth is the case is a black body which is absorbing that radiation, and therefore the temperature of the Earth is dependent on the radiation it is getting from the sun, right? So by that you have to know that how much energy is radiated per unit time from the sun. So you have the Stephen's law directly to get that value, that the energy radiated from the sun per second is equal to Q, let's say. Q equal to simply, so you know that the idea is epsilon E equal to epsilon A sigma T to the power 4, right? This is energy per time, and for black body epsilon equal to 1. So this is energy per time, is same as Q. So Q is basically now simply area times sigma T to the power 4, and the area of sun in this case is just because of spherical area, so 4 pi Ra square for sun. So AS we say because it is coming from the sun, and TS is the sun's temperature, so this is temperature is TS. So this is 4 pi Ra square into sigma into TS to the power of 4. So now this energy coming from the radiated from the sun, now it is contained in the whole circular orbital of the earth around the sun, right? Now at a certain position Earth is at a certain point of the orbit. So basically the Earth is, so you can think of it like this, that the that this sun is emitting radiation in all possible direction. By these yellow lines I am trying to show that it has radiation in all possible directions, and this radiation contains in the entire area of the circular orbital. So if this has a circular orbital shape, then the total thing is containing the radiation coming from the sun. But at a certain moment, the Earth is only at a certain point of the orbit here, let's say. So you can think of it like that the total radiation is being distributed in the total circular area of the orbital, but how much is Earth getting of that radiation at a certain moment is dependent on the Earth's position and the radius at that certain moment on that circular orbital. So basically if you think of it like that, so the total Q is distributed entirely in the whole circular orbital of radius r, which is the radius of the circular orbital. But Earth at a certain position on that orbital at a certain moment will receive only radiation of q divided by total area of the orbital 4 pi r square into the part that Earth is getting, portion Earth is getting of that total thing is pi into r e squared. So this is the thing, that the total radiation that is distributed over the entire area of the circular orbital. So that is why you take the energy per area per time as q by 4 pi r square, that the earth is possible to get possible to be obtained from the earth, and then how much is exactly falling on earth to actually increase its temperature is also obtained by multiplying this area dimension. So that is pi r square and not total 4 pi r squared, because we are only sitting at a particular portion. So that is why you multiply it by pi r e squared, and the total ratio then becomes q r e squared divided by 4 r square. So this is the radiation that earth will receive from sun. Radiation energy per time earth will receive from the sun. Now if there is to be a thermal equilibrium, okay, between the sun and the earth, so the rate at which the energy is received by the sun must be same as the rate at which the earth is also emitting that energy. So earth is also a black body, right? So whenever it is absorbing energy, it is also capable of emitting energy. And if earth has to be in a thermal equilibrium, then the rate at which it receives energy or absorbs energy from that sun's radiation has to be same as the rate at which it emits the energy from its surface, right? Now to obtain thermal equilibrium, rate of absorbing sun's radiation energy has to be equated to rate of emitting energy as radiation from Earth's surface. So therefore you have the rate of absorbing energy from sun by earth is just this one, because this is the energy per time. So basically this is the rate. So that you put in left hand side. So q r is r e squared by 4 r squared is equal to rate at which energy is being emitted by the earth. So again Stefan's-Boltzmann law has to be used. So energy per time is the emitting rate. So that is basically epsilon is again 1, because earth is also perfect black body considered. So just area times sigma t to the power 4 you have to put. So area is the area of the earth, which is like 4 pi r e square is the earth's radius into sigma into t is the temperature on earth. So this is T e to the power 4, right? So from here you get that you have to calculate Te, right? So you take T to one side. So T to the power 4 is basically Q. So yeah, So we have to put multiple expressions, but let us first simplify that. What is simply TE? So from here TE to the power 4 is Q RE squared by 4 R squared into 1 by 4 pi RE squared sigma. So this and this cancelling out. So you are getting Q by 16 pi R squared sigma. Now you have to also put the expression of Q here, because earlier we obtained from Sun the Q that is radiated is 4 pi Rs squared into sigma into Ts to the power 4. So that is what we put here, 4 pi Rs squared to sigma into Sun's temperature to Ts to the power 4 divided by 16 pi R square into sigma. So this sigma and sigma cancelling out, and 4 and 16 is 1 by 4, and pi cancelling out. So you are having Rs squared Ts to the power 4 divided by 4 R squared. So simply T to the power 4 is equal to Rs by 2R whole squared into Ts to the power 4. So from here you can put the values, necessary values, that first of all T is equal to then Ts into Rs by 2R. 2 by 4 is 1 by 2 to the power half. So Ts value is Sun's temperature. It is mentioned in the question that it 6 into 10 cube Kelvin into radius of Sun in kilometer unit. So if both are in kilometer, so in the ratio you don't have to consider the unit conversion, because both the units cancel out. So both are in kilometer unit, so you do not need to change that. So our Sun's radius was 7 into 10 to the power 5 in kilometer, and circular radius of the orbit was 1.5 into 10 to the power of 8 kilometers. So this is this cancelling out to the power half. We will get the value by calculating this will be 290 Kelvin. This is the temperature on Earth's surface after it reaches the thermal equilibrium. And when it reaches the thermal equilibrium, that when the energy at which it receives, the rate at which it receives energy or absorbs energy from Sun's radiation becomes equal to the rate at which it is emitting the radiation from its surface. So then Earth is reaching a thermal equilibrium, and then equilibrium temperature is T equal to 290 Kelvin. So hopefully this is clear. And this was an interesting question, slightly different from what we have right now solved till now. Okay, and other than that, there can be problems like, so the most of the patterns are covered already in the practice problems. So another thing, the pyrometer problem I can discuss. So second is about a optical pyrometer. So pyrometer, you can figure out that pyrometer is basically a particular instrument that you use to measure temperature, and normally you are familiar with thermocouple etc. that measures temperature by taking a temperature difference and generating a voltage, which the voltage, electrical voltage, will give you an estimate of how much is the temperature difference, and from that you can estimate the temperature. So that is a thermoelectric effect or Seebeck effect that is generally used to as used in thermocouples to actually get the temperature, sense the temperature. But other than that, thermocouple is an electrically controlled thing, and sometimes when the temperature is very high, there you cannot use a thermocouple, because that material of the thermocouple cannot sustain that much temperature. So in that high temperature operations, instead of thermocouple, pyrometers become very useful for measuring temperature. And pyrometer basically is operated by the idea of radiation, this radiation of the thermal radiation, that chapter that we are currently discussing. So whenever a body is heated up, thermally it is excited, so it emits a radiation, right? So from that, the pyrometer basically detects that radiation, and from that, because there is a relation between the wavelength of radiation and the temperature etc. that you already know from formula, Wien's displacement law etc. is there. So from that, by the direct correspondence from the spectral radiance intensity plot with wavelength, one can find out that how much is the temperature for a particular kind of radiation that is detected by the pyrometer. So that is how you measure temperature. But apart from that, this problem is based on a pyrometer's problem, so I thought this will be interesting. So the problem is that a radiation pyrometer in a room has a surroundings at a temperature of 300 Kelvin, and the pyrometer is focused on a black body at 600 Kelvin. So then the deflection observed in the galvanometer is 6 divisions, when it is pyrometer is focused on another black body, the deflection is found to be 400 divisions. Then they found the temperature of the later. So basically what happens is that there is a room where the room's temperature is 300 Kelvin. So this is the surroundings temperature 300 Kelvin. And in the room there is a black body number 1 and black body number 2. So both are black bodies. Now once the pyrometer, the optical pyrometer is once focused on this one. So pyrometer basically, whenever it is focused on a black body, based on its temperature, there is a certain deflection in the galvanometer of the pyrometer. So by calculating the division of deflection, you can calculate or you can get an idea how much is the temperature. So when it is focused on body 1, which is at temperature T1 is equal to 600 Kelvin, then the deflection, let's say D is equal to D1, let's say is equal to 6 divisions, okay. But when in the second case pyrometer is focused on the black body number 2, okay, we do not know the temperature of this, so T2 is equal to something that you need to calculate from the question. And but the deflection it reads in the galvanometer when it focuses on body 2 is D2 is equal to what is 400 division. So number of division is increased. So obviously it will be at a higher temperature, but we have to find out what is the temperature. And the room's temperature is 300. Now we can think of it like the room is in contact with the black body. So room is temperature T0 equal to 300 Kelvin. And you have to use that formula of Stephen's modified formula, that if two bodies, there is a black body at a temperature T and there is a surrounding of that body at a temperature T0, then the radiation that is emitted per unit time per unit area is just sigma T to the power 4 minus T0 to the power 4. This is the energy per area per time that is radiated from the black body, okay. So because you know that the galvanometer reading deflection, galvanometer reading deflection equal to D, it is the direct measure of how much energy radiated from the black body and detected by the pyrometer. Black body, in short BB I am writing, and detected by our pyrometer. So basically you can think of it like that they are directly proportional to each other. So D is directly proportional to Q, or D will be simply some constant, let's say K, T to the power 4 minus T0 to the power 4. So all other the integration, the proportionality constants and the sigma, this is also constant. So all these constants we combine and compile in a single constant value K. Because we do not bother about the constant term here. We are only concerned about the relation of D and T. So that is here. So K is all the constant compiled together. Total constant. Okay. Now the deflection is such that D1 is equal to initially 6 divisions, okay, and D2 is equal to 400 divisions. T1 is the body 1's temperature is 600 Kelvin and T2 is unknown and T0 is 300 Kelvin. So by using this expression, we write down our first equation is 6 equal to K times 600 to the power of 4 minus 300 to the power of 4. So from here you can get your value of K, right? And the second equation will be, second D2 is 400 is equal to K is same constant because it does not depend on the body type or deflection value or temperature or anything. K is just a constant independent of that, so it remains same for both of the cases. So in the second case, 400 divisions equal to K times, now this T2 is unknown, T2 to the power 4 minus T0 is again 300 because they are in the same room. So this is the case. Now you have to know what is this T2, right? So then if you take a ratio of 1 and 2, what it will give you is that 2 by 1 is equal to K T2 to the power 4 minus 300 to the power 4 divided by K 600 to the power 4 minus 300 to the power 4 is equal to 400 by 6. So from there, if you calculate it carefully, t to the power 4 minus 300 to the power 4 is simply 400 by 6 into 600 to the power 4 minus 300 to the power of 4. So you have to calculate, separate the terms from one side to other side, and therefore I am just writing down the final answer. You can check by yourself that T2 will come as 1687.3 Kelvin from that calculation. So this is the idea of how the it is not directly, you may not first identify this problem as a radiation problem, but you have to identify the type. That is why I wanted to uh, yeah, discuss some other problem. So pyrometer is basically similar problem, that you will find out that it is based on the radiation and detecting the radiation and just therefore detecting the temperature. So basic laws are the same, that you have to use a Stefan-Boltzmann law of radiation, and how it is dependent on the to the power 4 power of the temperature. But the only catch in this question was that you have to know that the pyrometer's reading of deflection in the galvanometer is actually the reading of the how much radiation energy is detected. So therefore they will be directly proportional to each other, so that you can get the equation or relation between the deflection D and the energy radiated with the temperature relation directly like this, and therefore you can solve your problem. So these are the simple fundamental concepts that we'll be needing for these kind of problems, and this will be the end of this discussion. I hope this will be helpful to you.